A very common way to predict and describe the structures of covalently bonded molecules and ions is using Lewis symbols and Lewis structures. A Lewis symbol is simply the symbol for a chemical element surrounded by one dot for each electron in the valence shell. For main group elements, we can have up to 4 pairs of dots, which represent the 2s orbital and the 3 2p orbitals. Covalent bonds are formed by sharing unpaired electrons between two atoms. So when two hydrogen atoms approach each other, they can pair the two electrons in a single bonding orbital between them. A connecting line is usually used to signify a bond formed by two shared electrons. Beryllium has 2 valence electrons, and each fluorine atom has 1 unpaired electron in its valence shell. So we can form BeF2 by creating 2 shared electron pairs. This still leaves 3 pairs of non-bonding electrons on each fluorine atom. Nitrogen has 5 valence electrons and 3 are unpaired, so we can form ammonia, or NH3, by making 3 new NH bonds, leaving 1 non-bonding lone pair on the nitrogen atom. Methane is CH4, and the formation of 4 CH bonds uses up all of the valence electrons on carbon. Water has 2 OH bonds, but also has 2 non-bonding lone pairs left over, and HF has 1 bond with 3 non-bonding lone pairs left over on the fluorine atom. For main group elements, in the second row of the periodic table, there is a strong tendency to form as many bonds as necessary to surround each atom with 8 electrons, because this is a particularly stable or low-energy configuration. The 8 electrons can be any combination of shared bonding electrons or non-bonding lone pairs. This is the octet rule. Sometimes the atoms can achieve this octet by forming double or triple bonds between the two atoms. For example, 2 oxygen atoms can come together to form a single bond, and this leaves each atom with 7 electrons. But if they share a second pair of electrons, each atom can achieve the octet configuration. The total bond energy between the 2 oxygen atoms is much stronger than a typical single bond energy, but not quite double the value. 2 nitrogen atoms form a triple bond with each other in N2. Triple bonds can also form between different elements, as in hydrogen cyanide. Sometimes it's useful to calculate a formal charge on the atoms. We can form nitric oxide cation, for example, by first taking an electron away from nitrogen to form the ion, and then forming a double bond to the O atom. This leaves the O atom with 8 valence electrons, but the N atom has only 6. So the O atom can donate one of its lone pairs to form a third bond to the N atom, and the octet rule is then satisfied for both atoms. To determine the formal charge on each atom, we count each non-bonding electron plus half of each bonding electron pair. This gives 5 for nitrogen, which is the normal number of valence electrons in the free atom. But oxygen has 5 also, which is 1 fewer than the free atom, so its formal charge is +1. Lewis notation is especially useful for describing the bond connectivity of organic compounds, because carbon is extremely flexible in forming single, double, and triple bonds. You will often encounter a shorthand Lewis notation where the skeleton of the molecule is indicated along with the double bonds. All of the endpoints and vertices are understood to be carbon atoms unless otherwise indicated, and the H atoms are omitted and simply understood to be present in sufficient quantity to satisfy the valence bond requirements. This becomes especially useful for large molecules like sodium lauryl sulfate, which contains 12 carbons and 25 hydrogen atoms. Sodium lauryl sulfate is a detergent commonly used in soaps, shampoos, and other personal care products. The shape of a molecule is often determined by minimizing the electron repulsion between bonding and non-bonding electrons. Acetylene, C2H2, can do this by adopting a linear geometry. Formaldehyde has 3 bonds, including a double bond to oxygen, so it can minimize electron repulsions by separating the bonds by about 120 degrees. Carbon dioxide is linear, but it's also helpful to remember that the terminal oxygen atoms each have two non-bonding lone pairs. If we look at these electron regions, we will see that the lone pairs are separated from the bonding electrons and from each other by about 120 degrees. Methane has 4 CH bonds, so they point to the corners of a tetrahedron to minimize repulsions. Ammonia has only 3 NH bonds, but the N atom has a lone pair. So if we look at the geometry of the electron regions, including bonding and non-bonding electrons, it is nearly tetrahedral. That means that the structure of the molecule must be pyramidal, not trigonal. Similarly, water has only 2 OH bonds, but also has 2 lone pairs. If the repulsion of bonding and non-bonding electrons were exactly the same, we would predict that the HOH angle would have the tetrahedral value, 109.5 degrees. The actual value is 104.5 degrees, indicating that bonding orbitals are a little bit more compact than the non-bonding orbitals. This model of predicting molecular structure based on electron repulsions is called the valence shell electron pair repulsion, or VSEPR theory. The shapes for central atoms having 5 and 6 electron regions are most useful for considering transition metal complexes. The presence of d electrons means that these compounds often seek to surround the central metal atom with 18 electrons instead of 8. Sometimes it's possible to write more than one equivalent Lewis structure for a molecule. In nitromethane, for example, we can achieve the octet rule around nitrogen and both oxygen atoms by formally transferring an electron from the N atom to one of the 2 O atoms and then forming a double bond with the other one. But both O atoms are equivalent, so a second structure is also possible. This situation is called resonance, and the system adopts a structure that is half of each. This type of resonance lowers the energy and enhances the stability of the molecule. The same thing happens with benzene, where the 3 CC double bonds could be in 2 different positions. We sometimes indicate this kind of resonance with a hexagon and a dashed circle inside to emphasize that all 6 CC bonds are equivalent. Trinitrotoluene, or TNT, is a widely used explosive. It has 3 nitro groups, each of which has 2 resonance structures, and it's built on a benzene ring with 2 additional resonance structures, so there are 16 possible resonance structures for this molecule. Lewis structures are useful for understanding why atoms form the number and types of bonds that they do to other atoms. The illustration of lone pairs of non-bonding electrons also helps us to understand why molecules adopt certain shapes as a result of electron repulsion. In our everyday work, chemists hardly ever use the dot notation, but Lewis structures have formed the basis of several shorthand notations that we commonly use to indicate the pattern of connectivity between atoms in molecules.